Welcome to the fascinating world of research methodology. Imagine you are a master chef walking into a brand new, fully stocked kitchen. To create a masterpiece, you need to know exactly what tools and ingredients you have. Understanding the different types of research is your very first step in becoming a brilliant researcher, as it helps you choose the perfect approach for your specific scientific question. Now that we have our kitchen analogy in mind, let us look at our first major classification, dividing research by its objective. Sometimes you just want to open the pantry and list exactly what ingredients are on the shelves. This is descriptive research, which aims to accurately portray a situation without changing it. Other times, you want to run experiments to find out exactly why a specific combination of flour and yeast makes a cake rise. This represents analytical research, which goes much deeper by testing hypotheses to explain exactly why something happens. Moving beyond our objectives, we also divide research by the type of data it uses. Think about how you evaluate your cooking. You might measure your flour in exact grams, which represents quantitative data. Quantitative research relies entirely on numerical data and statistical models. On the other hand, you might taste the soup to describe its rich, complex flavor profile. This represents qualitative research, which focuses on non-numerical data, like interviews and observations, to deeply understand human behavior and experiences. Another crucial way we categorize our work is by its real-world application. Basic research is conducted purely to expand human knowledge and build broad theories. It is like experimenting with new flavor combinations just to see what happens, without a specific menu in mind. Applied research, however, is specifically designed to solve an immediate, practical problem facing a society or industry. For example, if a medical team needs to urgently cure a new virus, they must use applied research to find a chemical solution quickly. Choosing the right application ensures your efforts are directed properly. You might be wondering, why do we need to categorize research so strictly? Choosing the correct type of research is exactly like choosing the right vehicle for a journey. A sports car is great for a paved racetrack, but it is absolutely terrible for climbing a rocky mountain. If you mistakenly use descriptive, qualitative research to cure a disease, you only end up with a beautifully written report about how patients feel, which cures nothing. Funding agencies, universities, and peer reviewers demand that you clearly state your research type because it dictates every single step of your methodology. To truly understand analytical and quantitative research, let us look at how we represent it mathematically. When we want to prove that one thing causes another, we build a statistical model, like the simple linear regression equation shown here. The symbol y represents the dependent variable, which is the final outcome we want to predict. X is the independent variable, the factor causing the change. Beta 0 is the y-intercept, showing the baseline value of y when x is 0. Beta 1 is the slope, telling us how much y changes for every 1 unit increase in x. Finally, epsilon is the error term, acknowledging that random factors also affect our outcome. If beta 1 increases, the cause and effect relationship is getting stronger. Now that we have our regression model, how do we actually find that crucial slope? We use this standard statistical formula. This equation calculates the slope, denoted by beta 1, by comparing how the variables move together. The numerator measures the covariance, which is how the two variables change together. The denominator measures the variance, or how spread out the x values are. X bar and Y bar represent the averages of the respective variables. If the variables consistently increase together, the numerator becomes a large positive number, resulting in a positive slope. This moves us beyond simple observation into mathematical proof. Let us apply these formulas to a practical scenario. A university professor wants to know if increasing study hours directly improves final exam scores. We are given data including exact hours studied and final grades. Our goal is to analytically prove that studying causes better grades. After plugging our classroom data into the complex slope formula we just saw, we calculate an intercept of 50 and a slope of 5. This simplifies our model to a clean equation. Y equals 50 plus 5 times x. This final answer tells us that a student studying 0 hours gets a baseline score of 50, and every additional hour increases their score by exactly 5 points. This perfectly demonstrates quantitative analytical research. That was analytical research. But what if our goal is much simpler? Imagine a completely different scenario where the school principal simply wants a summary report of the recent exams. The principal does not care why students passed or failed, nor do they want to predict future scores. They only want to know the current exact proportion of students who successfully passed. Because the principal only wants to know what is, rather than why it is, we use a descriptive quantitative research approach. We don't need complex regression models here. Instead, we use basic descriptive statistics to perfectly describe the current state of the classroom without making any assumptions about causes. To find this descriptive summary, we use the sample proportion formula. In this descriptive formula, the symbol p hat represents the sample proportion, which is the fraction of the group that shares a specific trait. The symbol x represents the number of successes, which in our case is the number of students who passed the exam. The symbol n represents the total sample size, or the total number of students in the entire class. If the number of passing students, x, increases, while the total class size, n, stays the same, the overall proportion will naturally increase. This gives us a precise numerical snapshot. Let us see this descriptive formula in action. We are given that out of a total class of 80 students, 60 students achieved a passing grade. We substitute our known values directly into the proportion formula. We replace x with 60, representing the successful students, and we replace n with 80, representing the total students in the room. Dividing 60 by 80 gives us a final decimal value of 0.75. This means exactly 75% of the students passed. We did not analyze causes or test theories. We simply described the reality of the classroom using undeniable statistical facts. Now that we have explored these concepts and calculations, let us look at how they all fit together in this flowchart. At the top, we have the broad field of research methodology. This branches into 3 main categorization strategies. On the left, we classify by objective, splitting into descriptive and analytical research. In the middle, we classify by data type, dividing into quantitative and qualitative research. Finally, on the right, we classify by application, separating into basic and applied research. This diagram serves as your mental map, helping you navigate the different paths you can take when designing your own scientific investigations. We have covered a lot of ground today, so let us review our key takeaways. First, understanding the different types of research is critical. You must decide if your goal is to simply describe a phenomenon or analytically uncover its hidden causes. Second, You must choose whether hard quantitative numbers or rich qualitative descriptions best answer your question. Finally, knowing whether you are conducting basic theory building or applied problem solving is essential. By mastering these distinctions, you ensure your methodology perfectly aligns with your scientific goals, leading you to valid and impactful discoveries. You are now ready to start your research journey.